four of my friends and I are going to mow a lawn that is 1,000 by 2,000 yards. It would take me 256 hours to mow it. Friend 1 would take 128 hours to mow it. Friend 2, half as long as that. 3, half as long as that. 4, half as long as that. So, how long would it take for all of us to mow? So there's a way to sort of intuit through this, and then let's see if we can come up with an equation based on our variation relationship. So I do know that I could do one lawn. So for me, I'm the same as friend 1. In fact, 2 of me is the same as friend 1. And for friend 2, it's like there are 4 of me. And for friend 3, it's like there are 8 of me. And for friend 4, it's like there are 16 of me. And so really what we're talking about is it's like we have, and then there's me, of course, right? So 7, 15, it's like there's 31 me's mowing this lawn. And some would say, oh, okay, well, it should take you, 31, a 31th of the time it would normally take you, which is 8.2 hours. Now let's see if our variation equation supports that idea. So, I do know that there is a relationship between the number of lawns I mow and the number of people and the rate per person and the time that they're mowing. And in fact, as the number of lawns, let me just use up for now. As if I want to mow more lawns, I can add more people, I can increase the rate, or I can increase the time. So in other words, this is all directly related to each of these. But each of these is inversely related to the other, meaning as the more people I add for the same number of lawns, I can slow down, or I could spend less time mowing. So the way we can construct this is we can say A, the number of lawns that we mow, is equal to N, is some constant times N for a number of people, or some constant times the rate, or some constant times the time. But in fact, it varies with all of these, and so we're going to treat it as direct with all of these being inverse to each other. The number of people times the rate times the time. But I have many different people with different rates, and so we would need to treat this as a composite. Well, the number of people at rate 1 times the time, plus the number of people at rate 2 times the time, plus the number of people at rate 3 times the time, plus the number of people at rate 4 times the time, plus the number of people at rate 5 times the time. Or looked at a different way, since there's only one of us for each of these, this is just the N1 or the N's are just ones. If we had more than one person, this would become more complicated. But there's one person at each rate, and so what we're really looking at here is time times rate 1 plus rate 2 plus rate 3 plus rate 4 plus rate 5. And so these rates are, well, 1 lawn per 256, 1 per 128 hours, 1 per 64 hours, 1 per 32 hours, 1 per 16 hours. You add that up times time and you get 1 lawn, because these rates are 1 lawn per this number of hours. You could have also done it by yards. You should have come up to the same thing. And so adding this, we need a common denominator. 256 is the common denominator, and so we end up with 1 equals t times 1 plus 2 plus 4 plus 8 plus 16 all over 256, equivalent to 31 256. So to solve here, we can multiply top and bottom by 256. Sorry, we can multiply top by 2, or the left and the right side by 256. Those divide out. And we can divide by 31. And those divide out, and we're left with t equals 256 over 31, which is exactly what I did to compute above when I said it would take me a 31th of my prior rate, a 31th of the 256 hours, so 8.2 hours. And the solution now can generalize to, well, what if you have multiple people at different rates? How does it work? Or what if they're not just a nice, clean percentage? You know, what if it's not doubling all the time? What if it's a less clean way that we can get our head around? So that is how you find rates.